going into the technical session, we have a small introductory session with the inaugural say formality. So I would now like to request our principal sir to please welcome the resource person. Sir, please.
Good evening to all. Thank you, Nivedita Madam, for organizing the seminar. Dr. Saptarshi Bej, welcome you on the virtual mode, but I request you, please come visit our college. As I mentioned, to request all our resource person. So one thing before telling something regarding Saptarshi Bej, I must express my sincere gratitude on behalf of the entire college family, because not only the seminar, because Dr. Bej has arranged so many resource person, IISER Kolkata, IISER Thiruvananthapuram, and others resource person, eminent, I can say, eminent resource person throughout India, I can say. So my sincere gratitude to you. And one thing is that the in near future, your friends, Paulos, I think, no, he has also delivered a
Yes,
very nice lecture. Yeah, Dr. Paulos, very nice lecture. And other resource person or senior most professor, they are very eminent in their particular respective field. So with these few words, I wish a grand success of the seminar, and the participants, those who come from other colleges, welcome you all, and we'll share more interesting topic in near future. Nivedita Madam will announce in better time regarding our plan, interactive session, invite lecture, whatever may be. So please give your feedback, particularly those from the other colleges. Definitely we'll share our other programs also. With these few words, once again, my sincere thanks to the organizing committee, with Madam Sandip Ponsa and other faculty members are there. So with these few words, I wish a grand success of this invite lecture. Thank you, ma'am. Over to ma'am.
Okay, thank you, sir, for your kind words. So let me introduce our esteemed resource person to our students and faculty members. Dr. SAPTARSHI Bej completed integrated bachelor's and master's degree in mathematics from IISER Kolkata in 2014 and PhD from the University of Rostock, Germany, with specialization in machine learning in the year 2021. He was also awarded the DAAT Prize for Outstanding Achievement of a Foreign Student by University of Rostock, Germany. He worked as the postdoctoral research associate in the Department of Systems Biology and Bioinformatics, University of Rostock, Germany, and subsequently from 2023, he is working as an assistant professor in the School of Data Sciences, IISER Thiruvananthapuram. He has published several research articles of international repute in high impact factor journals and also has several conference proceedings, PhD supervision ongoing, and invited lectures in reputed organizations to his credit. So I would now like to request Dr. Bej to please continue with the technical session. Sir, please.
Thank you, madam. Thank you, sir, for the kind introduction. I'm very privileged to be here. I'm very happy to contribute to this cause. So the topic of my talk today is how do machines learn. So as madam already told, that I did my specialization in the field of machine learning, and these days these terms, these machine learning models, the deep learning models, data science, these are actually affecting technological fields as well as industries, all sorts of directions. These models have influence on. So whichever field you are in, whether you are in technology, whether you are in education, it is always good to have a little bit of introduction or a little bit of introductory knowledge in machine learning. And the fundamental questions that we all wonder about is that how does this learning happen? So why do we call it machine learning? Are machines learning something, or in that case, how they are learning? So as madam told that the talk is going to be bilingual, so I will also switch in Bengali sometimes, but I will also try to speak most of the things in English. So here are some of the here is an outline of the talk. So I will actually present in dual mode. So I will use this kind of a presentation from my iPad, and then I will also switch sometimes to my laptop for showing you some coding or Python programming to actually convey what I want to say. So the first thing that we actually wonder about is that how does a child learn, and does it have any relationship with how machines learn? So মানে বাচ্চারা কিভাবে আর কি শেখে আর মেশিনরা আর কি কিভাবে শেখে আর কি, এই দুটোর মধ্যে কি কোনো সম্পর্ক আছে? এইভাবে যদি আমরা ভাবি আর কি ব্যাপারটা, তো বাচ্চাদেরকে আমরা মেইনলি যে দুটো জিনিস শেখাই সেটা হচ্ছে, একটা হচ্ছে রেকগনাইজিং অবজেক্টস. So we teach children how to recognize different objects, and we can also teach things like multiplication tables, right? So how do we teach children? So if we think about it, how do we teach children? So when we teach children, we actually show them several examples, right? So suppose we want to tell them the difference between or when there is a child, so we actually try to get them introduced to different objects, right? So we tell them that this is a dog, this is a cat, and even different kinds of fruits and vegetables and these kind of things, right? We show them examples. So this kind of thing, this is sort of a strategy, and we can notice a pattern, right, in this kind of a thing. তো আমরা যখন আর কি একটা আমরা ধরুন আমরা এই কুকুর এবং বেড়ালের মধ্যে আর কি একটা ডিফারেন্স মানে শেখাতে চাইছি একটা বাচ্চাকে যে কোনটা কুকুর কোনটা বিড়াল, তাহলে আমরা কি করি, প্রথমে আর কি বাচ্চাটাকে একটা কুকুর দেখিয়ে বলি এটা হলো একটা কুকুর, বা একটা বেড়াল দেখিয়ে বলি এটা হলো একটা বেড়াল, তাই তো? So first step is that we show several examples of objects. This is step number 1. যে আমরা যে অবজেক্টগুলোকে আমরা বাচ্চাটাকে শেখাতে চাই, সেই অবজেক্টগুলোর বিভিন্ন আমরা উদাহরণ দেখাই বাচ্চাটাকে, যে এটা হচ্ছে একটা কুকুর, এটা হচ্ছে একটা বেড়াল, এবং এটা হচ্ছে একটা ধরুন কোন রকমের সবজি হতে পারে বা যা খুশি হতে পারে। তো এটা হচ্ছে স্টেপ নাম্বার 1। এখানে আমরা এই জিনিসটা শেখাই। তারপর সেকেন্ড স্টেপে আমরা যেটা করি সেটা হচ্ছে আমরা প্রথম দেখা যায় যে বাচ্চাটা হয়তো ঠিকঠাক করে শিখতে পারছে না, মানে একটা কুকুরকে দেখাচ্ছি অথচ সে বলছে হয়তো যে এটা হচ্ছে একটা বিড়াল, বা একটা হয়তো আমি গাজর দেখাচ্ছি সে বলছে এটা হচ্ছে একটা ফুলকপি। তো বাচ্চা হয়তো মানে প্রথম বাচ্চারা আর কি শিখতে পারে না আর কি, অনেক ভুল করে আর কি। সো ইন দ্য ইনিশিয়াল ফেজেস দ্য চিলড্রেন উইল মেক সেভারাল মিস্টেকস, রাইট? সো সো আমরা বলতে পারি যে ইন দ্য ইনিশিয়াল phases children make several mistakes. And তারপরে সে ভুল করলে তখন আমরা কি করি, তখন আমরা সেটাকে শুধরে দিই আর কি, মানে এরকম ভাবে বলি যে না, যদি সে একটা কুকুরকে দেখিয়ে বললাম যে এটা কি, আর বাচ্চাটা বললো এটা হলো একটা বিড়াল, so we show the child a dog and ask the child that is this a dog or a cat. So the let's say the child says it's a cat, so then we correct the child, right? We tell it no, it's not a cat, you are wrong, this is a dog, right? So we correct the child in case there is a mistake, right? So correction in case of a mistake. So this is the basic learning protocol, right? So first thing is that we show several examples, and then we actually ask the child that what are so we ask and try to verify how much it has learned, and if the child hasn't learned, then we correct it, right? So if we think of these objects like a cat and a dog as some x, so x can be, let's say, cat, dog, or let's say carrot or a cauliflower. And then the child is something that is wanting to learn, right? And y is the predicted response of the child, right? So we can think of it like this, that we provide the child with some X, which can be cat or dog or carrot or cauliflower, and the child gives me replies, right? I show a cat, the child says it is a cat, that is fine. I show a dog, the child says it is a dog, that is fine. I again show the child a carrot, the child can say that this is a cauliflower, that is wrong. So I have to correct the child at that point. So I have to tell that no, this is not a carrot, you are wrong, this is a dog, right? So this is the process, and we do it repeatedly, so many times we do it, and then finally a child can learn so many different kinds of objects, right? So this is the basic learning procedure that we follow, right? So notice that this is the what we are actually essentially teaching the child is to classify things, right? So it actually knows that which is called what, right? In the world, this is our basic tendency, that we actually train a child to classify things, that which is a dog, which is a cat, which is a mother, which is father, and all these sort of things. So we have names for everything, and the child tries to classify and understand the difference between all these things, right? So we can think of this something like a classification task. We can call this a classification task, right? So here we are teaching a child how to do classification, right? Between different objects. Another kind of thing that we can also teach a child is let's say something like multiplication, right? So we teach a child multiplication tables, right? So child says 2 ones are 2, 2 twos are 4, 2 threes are 6, or maybe 3 ones are 3, 3 twos are 6, 3 threes are 9, and so on. And if you think about that, so there is this XY pattern, right? So X, then there is this X, and there is this child, and then there is this Y hat. So you might be wondering why I'm putting this symbol. I will explain in a little bit, right? So there is a difference between Y and this Y hat. So I will explain in a little bit why I'm putting this symbol, right? So so what happens is that when I ask a child that so when I'm trying to teach a child a multiplication table, so I am telling what is the X. X is, let's say, I'm asking it that what is 3 times 1, right? 3 ones are, then it is saying 3. And then actually I can say that I'm just taking the input as 1. So I'm just saying 3 ones are, then child replies 3. I'm saying 3 twos are, child replies 6. I'm saying 3 threes are, child replies 9, and so on, right? So here the problem is not like classification that we discussed before. So the problem here was classification, and this problem is a little bit different. Here there is 1, there is 2, there is 3, there is 4, and the child says that this is X, this is X, and this is Y hat, right? So when I say 3 ones are, child says it is 3. When I say 3 twos are, child says it is 6. When I say 3 threes are, child says it is 9, and so on, right? I can visualize this X and the relationship between X and Y as this straight line here, right? So this is how the multiplication table learning thing works, right? So this is sort of an example of something that we call regression, right? So these are 2 fundamental blocks of learning, this classification and regression, right? So these are the kind of problems that we actually try to teach a child, right? Now we can actually draw a parallel between this and how machines learn, right? So বাচ্চাদের তাহলে আমরা দুটো জিনিস বেসিক্যালি শেখানোর চেষ্টা করি। একটা হচ্ছে ক্লাসিফিকেশন, মানে যেটা হচ্ছে বিভিন্ন ধরনের বস্তুকে আর কি ডিফারেন্সিয়েট করতে শেখা, আর আরেকটা হচ্ছে রিগ্রেশনে কিরকম টাইপের ব্যাপারটা, যে আমি একটা হয়তো সংখ্যা বলছি, তার সাথে একটা ফাংশন আছে, সে আর কি বলছে যে হ্যাঁ 1 3 গুণ করলে হয়তো 3 আসছে, 2 এর সাথে 3 গুণ করলে 6 আসছে, এরকম ভাবে। এটা কিন্তু ঠিক ক্লাসিফিকেশন নয়, এটা একটু অন্য রকমের, তাই না? তাহলে এইখানে এই দুটোর মধ্যে একটু আছে, মানে এখানে এখানে অ্যাকচুয়ালি এক্সটা আমি বলবো রাদার হচ্ছে অবজেক্টস, আর ওয়াইটা হচ্ছে সেই অবজেক্টটা ঠিক কি সেটা বলতে পারে আর কি, মানে ওয়াই ক্যান বি ক্যাট অর ডগ or these are the responses, right? Responses. So I show different objects and I try to get their responses, right? তাহলে এই চিলড্রেনদের এই যে তিনটে শেখার স্টেপ, একটা হচ্ছে প্রত্যেকটা ডিফারেন্ট অবজেক্ট প্রচুর এক্সাম্পল দেখানো, এবং প্রত্যেকটা এক্সাম্পলকে আর কি শেখানো যে কোনটা কি, এবং ভুল করলে শুধরে দেওয়া। হ্যাঁ, এই তিনটে হচ্ছে খুব ইম্পর্টেন্ট আর কি স্টেপ। এবারে এইখান থেকে আমরা এটা ভাবতে পারি যে আমরা এবারে মেশিনকে কিভাবে শেখাবো। এই মেশিনকে শেখানোর স্টেপগুলো খুব সিমিলার।
Sorry to interrupt you, sir. Actually, one student has requested you to please explain the thing in English.
Oh, okay.
Yes, okay. Because he finds it very interesting, but he is not able to understand Bengali actually.
Oh, okay, no problem. So until now, what we covered is the difference between this classification and regression, right? The things that we actually try to teach children, right? So now I will actually speak a little bit about, I will try to draw a parallel between how we teach children and how we teach machines, right? So how to teach machines, right? One thing that you will notice here, I mean, the question is actually, can we draw a parallel between children versus machines, right? So can we draw a parallel between the learning of children and the learning of machines, right? So of course some of the facts are sort of similar. So machines we can also try to teach machines to classify different objects, right? We can try to teach machines to differentiate between a cat and a dog. So machines so basically, based on what we try to teach children, this similar kind of problem we can think how we can teach machines, right? So children, we can teach classification and regression kind of problems that I discussed already. So we can also teach machines, we try to teach machines classification, how to classify between objects and regression, right? So we can try to teach machines these kind of things. Okay, so how would a regression problem look like? Let's say in real life, let's say I am thinking that my x is let's say rainfall in millimeters, and y is production of rice, right? Production of rice, right? So what I do is that remember, for teaching children, first of all we need examples, right? We need to show them several examples of things. So examples means nothing but data, right? That's where the data in data science comes in, right? So we have to show them data, right? Data means, let's say over the past 50 years I have collected the data that what is the rainfall and what is the production of rice, right? So something like this. And then we see, and if I have we know how to draw a graph, right? So basically this is rainfall, which is basically x, and this is production of rice, which is basically y, right? So here you notice here that I am writing a y here and not a y hat, right? So there is a difference between these two. I will explain that later. Okay, so y is production of rice and x is rainfall, and over the past 50 years I have recorded the data, and I see that when the rainfall is low, the production of rice is also low. When the rainfall is high, the production of rice is also high. So I can observe that there is such a trend, right? So this is sort of some kind of data, right? So if I can show I can show that I am showing. So when I'm training a machine learning model, what I do is that I show that the rainfall, if the rainfall is like this, or if the x is like this, then the y would be somewhat like this. So if the x is like this, then the y would be somewhat like this, right? If the x is here, then the y would be here, the y would be more. If the x is maybe somewhere here, then the y would be somewhere here, right? So this is also just showing them different examples, right? And in this case also, so if the x is for children, if the x is 3, then the y is 9, right? If the x is 2, then the y is 6. If the x is 1, then the y is 3, right? This is how we actually teach children multiplication tables. That is also from some kind of data. We don't explicitly show them the data, but in real life situation this is more complex. Here we have some data, and using these x's we can show them multiple examples of such x's, and we can tell them that what should be the y value. So this is sort of something that is corresponding to this thing which we just called regression, right? Regression. So this is an example of that. And classification also we can say. For example, if we say that the x is, let's say BMI is body mass index, right? So the measure of BMI is weight divided by height square, and if the BMI is high, then you are likely to have diabetes, right? So, and let's say y is whether somebody has diabetes or not diabetes, right? So notice that here also the y is somewhat like classification, right? So there I am in case of the child, I am trying to teach the child the difference between a cat and a dog, right? And here in this case I am trying to teach the machine the difference between a diabetic patient and a non-diabetic patient based on the data BMI, right? So here let's say sort of I know that if the BMI is low, then diabetes is no, and if the BMI is high, then the diabetes is yes. So this is the y-axis, and this is the x-axis, which is basically nothing but BMI, right? So in case the diabetes is no, if in case the BMI is low, that is the x is low, then the values will be no, and in case the BMI is high, then the values mostly will be yes, right? So it will look somewhat like this, right? The data will look somewhat like this. So these are nothing but examples, and we want to show these examples one by one to the machine learning model until the machine learning model understands the relationship between x and y, right? So that is the idea, right? Now the thing is that one thing that we actually missed is that how sorry.
Yeah, no, sir, just carry on. I have told the participants if they have any questions to write in the chat box, right?
Oh, okay.
I think they will be, if they have any questions, they can ask you after the lecture.
Yes, please.
Right, sir? Okay.
Yes, please. So one thing that is important here is that for children, when they're making decisions, let's say, one thing that we don't understand is that how they are making the decision, right? So I am telling a child to understand the difference between a cat and a dog. I am showing the child several examples of cat and several examples of dog. Initially the child struggles a little bit to understand what is a cat and which is a dog, but gradually we see that something in their brain strikes, and it can then understand the difference between a cat and a dog, right? So what happens is that the child actually sort of subconsciously learns some patterns, right? Some kind of features it learns, right? Like for example, maybe that the tail of a cat, the tail of a dog is shorter and it's curved, right? Something like this it might observe. We don't know, right, how it actually learns between understands these kind of things, right? So these actually in the language of machine learning we actually called them as features, right? So these are the kind of things that a child actually inherently understands, but we don't know actually that how to actually teach them. We don't explicitly teach these things to to a child, right? But in case of machine learning, what we do is that there is this. So the rest of the steps that we follow. For example, several examples. We show several examples of the objects, and then we actually try to see that what is the prediction of the child, and then we make a correction in case the prediction is wrong, right? So these three steps are the same, but we also have to specify a model actually. So the problem is that for example, when this is y and this is x, so this is rainfall and this is production of rice, let's say. We see that there is this linear dependence between the rainfall and the production of rice. So what we can say is that there are actually there is this intricate relationship between mathematics and real life events, right? So for example, we know that there are several kinds of mathematical functions, right? So for example, when we say simple harmonic motion, then if you are a student of physics, so simple harmonic motion, it actually can be modeled by simple harmonic motion can be modeled by a periodic function. For example, we can write like a sine omega t plus phi, right? So what does it give us? So if this is y equal to a sine omega t plus phi, or we can just say that that this is y equal to a sine omega x plus phi, right? So we put in an x and we get a y, right? So this is how the model works, right? So this is how actually mathematics is sort of related to real life. Another example you can think of is let's say bacterial colony formation. So let's say there is one bacteria, and from that it divides into two bacteria. From that it divides into four bacteria, and so on. So let's say after 100 generations, how many bacteria will be there? We can say that this can be actually modeled by. So if I want to predict some y, which is the number of bacteria after 100, this is that is actually 2 to the power 100, right? If instead of one bacteria, we could if instead of one bacteria dividing into two bacteria, we had one bacteria dividing into three bacteria, then this would actually change, right? So this would then be y equal to 3 to the power 100, right? No longer 2 to the power 100. So in general, we can say that this situation can be modeled by equation which looks like y equal to a to the power n, where n is the number of generations and a is the number of bacteria, or a is the number of one bacteria, dividing into how many bacteria in one single time. So if we actually talk about disease propagation models, that those are also very similar to this. Why I am saying this is that is actually to draw your attention to the fact that several real life events or several real life situations can be modeled using this kind of mathematical equations, right? So the mathematical equations we already saw were, let's say, a sine omega t plus phi, or omega x plus phi, let's say omega x plus phi, or maybe we can say y equal to let's say a to the power n, or things like this, right? This is a sinusoidal function. This is also, you can know from the we know that from Newton's law, we can also this ux plus half fx square, right? So this is, if this is the this is the displacement, and this is the initial position, and then this is this is initial time point. So if I actually I think the actual equation is written as s equal to ut plus half ft square, where f is the acceleration, u is the initial velocity, and so on, right? And t is the time. So if I put, so this is basically s of t. This is a function of t, right? And it is written as this. So the thing is that the main point here is that there are all these mathematical equations that can model real life situations, and these mathematical equations have several parameters. And if we can fix these parameters, then we can actually model a real life situation. An example is that here, let's say in the first case, there can be an oscillator which is oscillating. Let's say the amplitude is, let's say, very small. So I have, let's say, one pendulum which actually oscillates like this, and another pendulum I have which, let's say, has a much larger amplitude. It oscillates like this, right? So in this case, this a will be smaller because this a actually models the amplitude, and in this case this a will be larger, right? Very similarly, we also, let's say, we were actually thinking of our data, which was actually looking like this. This is x and this is y, right? X is, let's say, the rainfall, and y is the production of rice. So this is a trend. And what mathematical function actually can model this kind of a situation? There is a mathematical function, right? And that function is basically a linear function. It's basically nothing but y equal to mx plus c, we write, or I can also write ax plus b, right? So this is basically y equal to ax plus b, right? So it's a linear equation, and we can actually model this using a linear function, right? So how would that look like? So if I, you know what this a and what this b is, right? So what a is the slope. So when we write like this, we can say that this is x and this is y. If I plot this ax equal to b, so we actually say that this quantity is the intercept. This yellow part is the intercept, and this angle, this theta, that is that represents the slope of the line, right? So the slope and the intercept, right? So notice that if we change this a and b, then the line also changes, right? So if I take, instead of this line, if I actually choose this line, and if I choose, let's say, maybe this red line, so the red line has a different theta and a different slope, right? So in this case, the problem is that we have to understand that what is this a and what is this b. So that is the main goal of this problem. That for example, in this case, we have to understand that what is the amplitude. So here the amplitude is low, so maybe we have to figure out that what is the amplitude, what is the proper amplitude to model this situation, and what is the proper amplitude to model this situation. And in this case, we have to figure out that what is the a and what is the b, to actually see that which is the model that actually can fit this data, right? For example, if we think that this is a straight line, if I say that this is a straight line that can model this data, that would not be very correct, right? I would say that if I take this straight line, that would be a much better model for this data, right? And why I say model, because this is the actual data. Whatever are the white dots, that those are the actual data. And if we want to create a model, then that is the modeled data. So here, for example, if this is a particular x, then my prediction as per my model would be this. For if I take this yellow model, and this is my, let's say, xk, then the prediction as per my model will be this yk, right? And this yk, which is the prediction as per my model, to actually denote the prediction separately, we actually put this hat on top of y. So there is a real y which actually tells you that what was the real rainfall over different rice productions. So what were the different rice productions over different measurements of rainfall, and then there is this model that can actually tell you that if I give some x, then what would be the y for that, right? So there has to be, in machine learning, what we actually follow is that we actually follow this approach, that we model a situation using a mathematical equation, right? And these models have different parameters, right? For example, this a and b, these are different parameters of the model, right? And we try to understand that which choice of parameters is actually sort of best for our data, right? In this case, this choice of this model, which has its particular a and particular b. So for example, the b the a, that is the slope of this model, would be this theta, and the slope of this yellow model would be this theta. And I can say that this yellow theta is definitely better than this red theta, right? Because the red theta does not fit very well with the data, right? Now, when I say that it does not fit very well with the data, how do I understand that it does not fit very well with the data, right? We can understand that by measuring errors, right? For example, if I have this model, let's say for this same data point, let's say if I actually consider this white data point here, let's say this data point, according to the yellow model, what is the error? What should be the error of my prediction? The error of my prediction would be this much, right? So if I just take this point, if I think about the x corresponding to this white point, so this is the x corresponding to this white point, and this is the y, right? And in that case, the prediction of my model actually deviates from the prediction from my actual data by this much. So this is this point. So if I think of this as an xk, then this would be my yk, and this would be, this point here would be my y hat k, right? Because this is the prediction. This is the prediction made by the model. This is the actual value, and this is the x, right? So my job is to put an x into the model. The model will predict some y. This is the y, and then I measure that how much that deviates from the from this actual value of y, right? In this case, the deviation is this much, this yellow line here, right? However, if I think of the red model, if I think of this red model, then the same error would be this much, right? So this is actually, if I think of the red model, then this is, as per the red model, this should be the y hat k, right? This much is the deviation from the reality, and in this case, this much is the deviation from the reality. And if I sum over these deviations over all of these data points, if I sum over this kind of deviations over all of these data points, then I will see that the sum of the deviations is actually much lesser for the yellow model compared to the red model, right? And that is sort of this measurement of how much my model deviates from reality, right? It's just like correcting a child of the errors that the child did, right? So if the child is, I'm showing a cat and the child says that it is a dog, then I have to sort of counter the child and tell it, no, you are wrong, it is a cat. I have to, and in a similar way, for a machine learning model, what we need to do is to teach the machine learning model that how much error it did, right? And there has to be a function that actually measures the error. So I hope that you actually got the difference between this y and y hat. Y is the reality the real data that is there, right? That means that X is rainfall and Y is the amount of rice prediction, amount of rice produced, that is recorded as per the data, and Y hat is the predicted rice production as per the model. So there is a difference between the two, right? And we can actually devise one function which we can call as loss. So we can write this as the loss function. The loss function actually measures the difference between the reality and the predicted or prediction. So reality is Y and prediction is Y hat, right? So the loss can be thought of as the absolute difference, or you can also take squared difference, because loss cannot have negative values, should not have negative values. So here we can take the difference between reality and prediction, right? So now let us revisit. Now you can sort of understand the approach a little bit. That when I was actually talking of a child, we did not know that how the child relates between the X and Y, right? We just try to teach it that by showing examples of cat and dog. It does not know how to relate between X and Y, right? X is an object, I show it, and Y is the response that the child gives, right? I show it an object, the child says it is a cat and dog, but it does not. I do not know how it relates, right? But here I am giving actually the model. I am giving it a way to actually relate between X and Y. What is that? That is this equation. Using this equation, it actually relates between X and Y, right? And so the first step in this case is this modeling, right? Modeling is something that relates between. Sorry.
Yeah, I will request all of the participants to please keep muted. Chittaranjan sir, please mute yourself. Okay, I have sir muted. Yes, sir, please carry on, sir.
Right.
Sorry for the interruption, sir.
No worries. So modeling actually relates between some X and some Y, and then we actually do the learning thing. Learning is showing examples, measuring. So let me write this a little bit in a little bit more detail. So this is sort of the algorithm that we want to follow, right? We have some data that is let's say x1 ... xn, and we know the corresponding y1 ... yn, right? So we have some data, some X and some Y. These are the examples, right? And so what should be the input and what should be the output, right? So this is X and this is Y. So we can write this as X and we can write this as Y. And then we have a model that actually tells me that what should be the relationship between X and Y. That depends on what kind of real life problem I want to model, right? If it is a simple harmonic oscillation, then it is a sine function or a cosine function. If this is let's say rainfall versus rice production, then this is a linear function, and so on. So basically this actually tells me a model that it tells me that how I should relate between X and Y. That is let's say Y equal to AX plus B, and then is actually we actually use measurements, right? So measurements of errors, right? So in this case, what we do is that in this case, when we measure the error, we actually put all these examples in these models, right? So we actually so this is actually Y hat, right? So from this equation, what we can do is that we can say Y hat of 1 is equal to A x1 plus B. So this x1 I put into the model. Y hat 2 is equal to A x2 plus B, right? Like this. And then we actually do this for all the n points. So A xn plus B. right? So if we can do this for all the endpoints, then we can actually get the predicted values of y for all these points. And remember, these are the real values of y. So we have the real values of y, we have the predicted values of y, and thereby for every value of y from I equal to 1 to n, actually we can measure some kind of loss, right? So this is what we can do. But what does the loss, what do we do with the loss, right? So the loss actually tells us that how much the prediction actually deviates from the how much the reality actually deviates from the prediction, right? Prediction of the model, right? So remember that for children also we correct, we try to correct the children, right? So when they say something wrong, we correct the children, right? So here also we have to correct the model, right? But what does it mean to correct the model, right? So initially, let's say for these two models, we had this x, so which was we had this red model and this yellow model, and of course in these two models, what are the things that are different? The things that are different are this a and b, right? For this model, the slope and the intercept is different. For this model, the slope and the intercept is different. The slope and the intercept itself determines that how this line will be, right? So whether this line will be parallel to the x-axis or like this, whatever is this theta, that actually decides that what should be the orientation of the model, or which a and b are actually the best fit for this data, which a and b actually can minimize the loss, right? So here, after we have calculated the loss, what we have to do is that we have to find, or we have to change the a and b. If the loss is high, that means the reality is far away from the prediction, and in that case we have to figure out a way that how we can reduce the loss or reduce the difference between reality and prediction. So what we can do in our approach, that in the beginning we can actually choose that a is a random number and b is a random number. So if we take two random numbers a and b, we can create a model which is y hat equal to ax plus b, right? And using that model, we can actually see that what should be the predictions of that model. Using those predictions, we can measure that how much this model, how much the reality deviates from the predictions of the model. And using this loss, we should actually figure out that what should be the new a and b. So we have this old a and b. So this is a old, b old. So we have old a and b, and using old a and b, I'm actually creating this model. And ultimately, I have to figure out that what should be the new a and b, and that is done using this using a learning algorithm which is called the gradient descent algorithm. So it actually says that the new a and b can be calculated as old a and b minus some learning rate times the gradient of the loss function with respect to a, and here also b new should also be b old minus gradient of the loss function with respect to b, right? So this is the idea, and using this new a and b, we will repeat this entire process again, right? And now the question is that what is this new equation, right? So the gradient descent equation, right? What does it do? So the gradient descent equation, so what it does is that if I actually measure, so this is the loss function, if you remember, so this is the loss function, and if I measure the gradient of the loss function with respect to, let's say, with respect to a, that means that what I do is that that how much, in what direction I should change a so that this loss function is maximized, right? So that is the direction in which I need to move the a, right? Ultimately, what is happening here is that this loss, I'm visualizing this loss as a function of a, because if I change a, then my y hat should change, right? Because here I change a, the y hat will change. And if I change the y hat here, then the loss will also change. So basically what we are seeing is that the loss is actually a function of A, and the loss is also a function of B, right? The loss is also a function of B, right? So I need to find the A and B for which the loss is actually minimum, right? So I start with random A, if you remember. So I choose, in the beginning I choose A randomly, and then I try to move A in such a direction that I can minimize the loss. So here, let's say, here is the minimum loss. So I start with random A, and then with different iterations, I try to move to a point where A is such that the loss is minimum. Similarly for B, I can start with a random value of B, and then I try to move towards a point, or move towards a B for which this loss is minimum. And the loss being minimum means that the difference between reality and the prediction is minimum, right? So that is how we are sort of trying to play the game here. So, and then how do we summarize this? So first of all, there is a real life situation, right? And we choose a mathematical equation that is sort of appropriate to model that real life situation, right? And that mathematical equations has some parameters, right? Those parameters determine what is the behavior of that mathematical equation, right? For example, for a linear regression, those parameters are A and B. For a straight line, those parameters are the slope and the intercept. The slope and the intercept actually decides that what should be this, and then after that, what we do is that we train the model. That means that we show the model the examples from the data that we have, and then we measure the difference between the reality and the prediction. So how much my real data actually has deviated from the how much my predictions have deviated from the reality. Once I have that, what we do is that we try to update the model. We try to update the model, right? So, and that updation step is done using the equations of gradient descent, and that is what we actually called learning, right? So what I want to do is that I want to show you that whatever I told, how it pans out to be if we want to if we try to code that in Python, right? So let me share my screen with you. So I hope you can see my screen. So here, if you see the screen, so here, let's say I have this X and Y. So this is some X and this is some Y, right? And ideally, I should have a line which looks like this, right? This should be my ideal model, right? And how do we actually sort of achieve this? Is that remember this loss function that we actually talked about. So loss is the difference between Y and Y hat. So here we have just put a square on that so that we don't have negative losses. And if we sum up the losses over the examples, then we have a positive loss. And if we actually calculate if we partially differentiate the loss with respect to A and B, then we know that in what direction we should change the A and B to actually minimize the loss, right? So that is the equation of gradient descent, right? And then what we do is that we start with this random guess for A and Y. So I have this A, which is a random number. I have this B, which is also a random number, right? Remember, we are doing the prediction in terms of A and B, right? So Y equal to A plus BX, right? So our model is Y equal to A plus BX, right? So I started with a random A and B. So this is random A, this is random B. And if I have a look at this, then my model actually looks like this, right? So the pink line is the model and this is my data, right? Ideally, the model should look somewhat like this, but it is not looking like this. It is looking like this. So here, now we have to tell that my prediction, which is this pink line, is basically my Y hat, right? And this is my actual data, right? I have to tell the model that this my prediction is actually way too far from the real data, right? So in that case, what do we do is that we actually apply this equation. This equation is this B new. So I have not written the new here. B new is equal to B old minus the learning rate times the gradient, right? The gradient of the loss function with respect to B. So we have calculated the gradient of the loss function with respect to B, and this is the formula for the gradient of the loss function with respect to B, and that has been just written here using the code. And here also the gradient of the loss function, the equation is the same. The new A is given by the old A minus the learning rate times the gradient of the loss function with respect to A, right? So this is the gradient of the loss function with respect to A, and I have just written it here, right? So this is the updated A and B. So initially my A was 0.548 and my B was 0.715, but after updating the A and B using this gradient descent equation, which actually changes this A and B in such a way that the loss is minimized, and here is this new A and B. Before the A was 0.54, now the A has become 0.57. Before the B was 0.71, now the B has become 1.07, right? And if I look at the plot here, then I see that here the line was a little bit, more far away from the data. It is a little bit inclined like this, and in this case the line has gone a little bit up. I don't know whether you can notice. But now my new A and B is 0.57 and 1.07. But if I again apply the same equation on this new A and B, so if I again apply the same equation, the equations are the same. This equation is the updating equation for B. This equation is the updating equation for A. I again apply the same equations on the new A and B. And again, I have another set of new A and B. Now the A is 0.59 and the B is 1.38. Previously, the B was 1.07, for example. Now, if I again look at the change, then I can see that the line is again aligning a little bit more with the data, right? So what I do is that if you look at this plot here, initially my prediction is very far away from the data. Now I adjust the A and B a little bit, and my prediction becomes a little bit near to the data. I adjust the A and B further, my model becomes nearer to the data. And now if I say I am just mechanically doing it by hand 3 times, I showed you by updating, I now just write equation 150 times, right? In this case, the same thing is being done 150 times. So we start with a random A and B, then I update the A and B in such a way that the loss is minimized, right? So if I can do that, and finally I get this A to be 0.76 and 3.23, right? So this is my final A and B. Remember, I started with a random A and B, which was 0.54 and 0.71. And after doing this process, the learning process several times, we get 0.76 and 3.23. And if I actually use this A and B for my prediction, the final A and B for my prediction, then my model will look like some problem happened. So let me cell run all above. So if I run this A and B 150 times, then I see that the model, this line, the red line that you can see, is actually no, in this case the line is Y. So I just want to plot this Y2. Y2 is the line that I constructed. So Y2 is this A plus BX. So if I just run this is the black line. So this is what I learned. So my model started from here, this line. Now it is gradually aligning to the data, and finally it aligns to the data just like this, right? And if I actually observe the loss over the entire period, remember that what I am trying to do is to reduce the loss, that is to reduce the difference between reality and prediction. And I see that the loss is actually decreasing uniformly. So I actually created a visual GIF file to look at this, and if you can see that here, you can see that how this model, sort of starting with random A and B, it is learning uh, at every iteration, it is learning a new A and B, and is learning how to minimize this loss, right? So this is one example, just one example, that how to actually train a machine learning algorithm. The basic principle of training a machine learning algorithm. Similar things can also be done for other models, for example, the logistic regression model. So here also, if you look at the data distribution, here the X and Y are sort of a little bit different, looking a little bit different. This is an example of the classification problem we talked about. You can imagine that X is BMI and Y is, let's say, whether a patient has diabetes or not. And in case there is a patient has low BMI, they have a chance of having they have no chance of having diabetes, that is 0. And in case the BMI is high, then the chance of diabetes is high, that is 1, right? So it is a 0-1 kind of a data. It's not a regression, and it's not a regression kind of a data. It's a classification model. And in this case, we see that the same principle can be applied in this case also, the gradient descent equation. And here the mathematical model is no longer a straight line. The mathematical model is a logistic function, right? So in the previous case, the mathematical model was just y equal to mx plus c. So the y hat was, in this case, the y hat was mx, y hat was a plus bx, right? In this case, y hat was a plus bx. But in this case, the y hat is a little bit more complex function, which looks like this. And this function is useful if you are modeling such a distribution. It looks like an S, and that S is between 0 and 1. So, but the principle of learning actually is basically the same. So just to conclude, I think I'm a little bit over time now. So just to conclude, what we just learned here is that if we want to learn from data, then first of all we have to choose a model that is relevant. If there is an X, if there is a Y, right? So we have to choose a mathematical model that in general can relate between X and Y. This model has several parameters, and by the learning process, what we do is that we start with random parameters, right? And then what we do is that using those random parameters, we measure the loss, that how much the prediction of the model deviates from the reality, and then we actually change those parameters in an attempt to minimize the loss, right? And this process itself is actually the fundamental process of learning. It is followed by let's say linear regression models, logistic regression, or even neural networks also follow the same gradient descent equation and the same approach to learn from data. That is what we actually call learning. So with this, I would like to thank the audience. I wish I would have more time to actually convey some more things in a little bit of detail. I actually feel now that the things were a little bit hurried, but in any case, I have to conclude for now. But I hope that I could actually at least convey to you the basic idea of what we call learning in the sense of machine learning. Thank you.
Yes, thank you. It was really nice, and I think there was a glimpse of everything in it. There were the equations which you have used, as well as the application, and finally the setting was very fascinating. So, so thank you for giving all the glimpses in 1 hour. So we are not going to leave you. We will be having other lectures as well. Then we can have a detailed study so that students can get a very good glimpse of the same. So it was really nice. So since we have very less time, we can take 1 to 2 questions from students if they have, or we also have designed the feedback form of our students. They can also send the questions, which I will communicate to you by the email. So if any of the students have any question, they can just ask. We can take only 1 or 2 questions, and rest of them can be given in the email. So only the relevant questions can be asked, right? So any of the students has any questions? So I can see the chat box. Students are very much happy and they are thanking you, sir. So it is so nice. And I think if any of the students has any questions, they can ask now. So I cannot see any hand actually raised. So I think we can take up the questions in the email, because students will be given the link of this, say, video. And the useful part is that they will be able to go through again and again, and then they will be able to frame the questions or their queries, if any. So it was really nice to have you, sir. We will also like to have one faculty development program with you and Dr. Paulos, which I have talked in January. So it will be so nice for our faculty members to get into the new glimpse. And I would say the machine learning has an interdisciplinary dimension, and which is the one of the objectives of the Department of Biotechnology, this DBT Star College scheme. So on behalf of the entire college family, I would like to thank you again for accepting our invitation. Especially this has been possible by our honorable principal, sir, who gave your contact to us, and also to you for giving the contact of many resource persons, which we have conducted, and we are conducting the invited lectures. Sir, please.
Thank you very much, madam.
Yes. It was really nice, and I will be sharing the link of the YouTube link as soon as it is ready, so that with all of the participants and also the feedback which we receive from the participants, this will help us in the improvement of the knowledge of the students.
Absolutely.
Yes. So it was really nice, sir. Thank you all.
Thank you very much
for joining, and we can just wind up the session for now. And we are not actually ending; we are connecting with sir.
Absolutely.
Yes, sir. Thank you, sir.
Thank you.
Thank you,
Okay, then bye everyone. Have a nice evening.
Thank you very much, sir.
Thank you, sir.